This is a review of integration by parts, a method to help solve more complex antiderivatives. Integration by parts helps us solve integrals that cannot be solved by a simple substitution. Consider the following integral, where we have x sine of x squared that we want to take the antiderivative of. We know we can do a simple u-substitution by letting u equal x squared and du equaling 2x. We can replace dx with the substitution and have a much simpler antiderivative, which is 1/2 the sine of u du. However, by looking at something very similar, that is the antiderivative of x sine of x dx, we can see that a simple u substitution will not be enough. Instead, we can use this using the method of integration by parts. This technique of integration by parts is based off of the product rule. So the product rule that we are familiar with in our derivative rules for calculus is that we have some function of x which is comprised of two different functions of x. That derivative then is the derivative of the first times the second plus the derivative of the second times the first. We can then apply this by taking the integration by parts method in a new level. We can take the antiderivative of both sides of this equation and find the following, that the antiderivative of our h prime of x will just be h of x, which we know is equal to f of x g of x. Taking the antiderivative of our f prime of x g of x plus our antiderivative of our g prime of x times f of x. We will then be able to solve for our antiderivative of f of x g prime of x and come up with the following equation. You may see integration by parts written in this form, but you can also make the following substitutions for an equivalent, more simple equation. So if we let u equal our f of x and let dv equal our g of x, then our du, or the derivative of u with respect to x, will be our f prime of x, our derivative of that function, and our v will be our antiderivative of our dv function, or our g prime of x. Thus, we have the following simplified compact equation for integration by parts, which is that the integral of u dv is equal to uv minus the integral of v du. So consider again our original integral, the antiderivative of x sine of x dx. We will want to apply the integration by parts method. We can let u equal our x and dv equal our sine of x. Our du is then the derivative of x, which is 1, and our v is equal to the antiderivative of sine of x, which is negative cosine of x. Then, plugging back in, we can substitute for our original equation. So, comparing these two, we have u as our x and sine of x as our dv. So we can substitute back in uv, or x, negative cosine of x, minus the integral of v, negative cosine of x, times 1 dx. We can simplify this by combining our negatives and grouping terms together to have negative x cosine of x plus the integral of cosine of x dx. This integral cosine of x dx is a basic antiderivative that we can do, which goes directly into sine of x. Now, because this was an indefinite integral, we need to remember to add our constant. This correctly would have been done in previous steps, but we've chosen to simplify and remember to bring it in at the very end. Alternatively, had this been a definite integral, meaning that it is bounded above and below by some other value, then we can apply the fundamental theorem of calculus by evaluating our final answer from b to a, meaning that we will take the negative b cosine of b plus sine of b minus negative c cosine of c plus sine of c. So this is the overview how we can use integration by parts. But you might be asking yourself, how did I know which substitutions to make for u and v? So we will discuss how we can choose our u, which is of course some function of x. So the acronym LIGHT can be really helpful to visualize what choices to make. Again, this won't always be perfect, as some functions might be a combination of other functions, but it is a great starting point while we're getting more familiar with integration by parts. So, in descending order, we'll prioritize choosing our u of x for logarithmic cases, such as the natural log of x. This being because we can't easily take the antiderivative of the natural log of x. Further, we'll continue down. We'll choose inverse trigonometric functions next, then algebraic, then trigonometric, then exponential. So by making these choices for u of x, we'll simplify the process of doing our integration by parts. As an example of choosing u and our dv, consider the antiderivative of the natural log of x over x cubed. We can rewrite this to a simpler form and let u equal our natural log of x. This is a logarithmic function and should take priority as the function we would choose for u. Our dv must be the remainders of the integral and will be our x to the negative 3 dx. We'll take the derivative of our u, or our natural log of x, to get 1 over x dx, and our v will be the antiderivative of x to the negative 3, leaving us with a v of negative 1/2 x to the negative 2. We can plug this into our integration by parts equation formula and have a much simpler integral to solve than we had before. 1/2 x to the negative 3 can be solved using our basic integration methods. As a review, remember to use integration by parts when you have the product of two unrelated functions you want to find the antiderivative of. This technique will be essential as you continue developing your integration methods for all future classes using integration.